This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, let's get started. The class seems to be getting smaller and smaller. I assume people are watching online. I hope anyway. Now there are a few questions on the LMS discussion board. I'd encourage you to take a look. People have been asking questions about various topics that have been discussed in the lectures and in the workshops. If you have any if you still have questions that need answering or you don't think the answers are very good, you're welcome to come to me after the lecture or something, and I can get more involved in some of the questions if that makes sense. But please make sure you have a look, because this is supplementing the material, and other people are going to have questions that are really relevant to anything that you might have confusion on as well. Today we're moving on to a different topic. So this is n-gram language models. So yesterday we looked at classification, looking at a text, trying to classify a label for that text as a whole. N-gram language models are more about the idea of assigning a probability to a sequence of words, which actually is framed as a kind of classification task, as we'll see later, which is part of the reason why we have it here. It's a separate topic unto itself, and it's going to relate into some of the other topics that we see later. So the idea here is if we're given a string, a sentence, say, we want to be able to say, is this a good example of the language or is it a bad example? So it's a bit like trying to say, is this valid English or is it not? Or is this valid Chinese, is it not? But we'd also like to give it a number to say, well, this looks sort of bad. This looks not perfect, so we give it a slightly lower number, say. This looks very bad, we'll give it a very, very low number. And this can help in a lot of settings. So I've got a few listed here. Things like speech transcription, so automatic speech recognition. Things like spelling correction, machine translation, query completion. These are all tasks where the computer has to predict a string. It has to actually generate language. So yesterday we were talking about taking language as an input and generating a machine interpretable label. In this case, we're saying, let's try and actually generate the language itself. It's super loud. It's making a funny noise. And so the idea, if we have this system that can say, this looks like a good string in the language, this looks like a poor string in the language, then we can use this inside these generation scenarios. Now, there are other generation tasks, things like summarization and dialogue systems. I'll just say a quick word about that. So summarization is when you have a document, you're trying to distill it down into a shorter version. You might do that by just copying bits of the text, but you might also do this as a generation step where you're actually creating new sentences, or you're gluing together phrases from the document into different sentences that you wouldn't have seen in the document. So this is another case where we're doing something similar to language models, and we might actually use language models formally inside of a pipeline that does this. Dialogue systems are things like Alexa chatbots, Google Home, these kind of things, Google Assistant. The idea is that you're having chit-chat back and forth with the machine. It needs to be able to generate language to respond to you. So this is another scenario where being able to say, this is what the machine proposes. Well, is this actually a good example of language, or can we do better? And this is where a language model comes in. Okay. So what we're going to cover today is the idea of n-gram language models. There are other types of language models. We're going to talk about n-grams today. These were state-of-the-art until maybe 5 or 6 years ago. And now there's been a very big push towards deep learning type language models or recurrent neural network language models, which have a slightly different formulation. And we'll touch on those later in the subject. So n-gram language models, you might have seen these as Markov models in some of your other studies. This idea is a relatively simple one for assigning a probability to something that's very long by decomposing it into smaller steps. It's the chain rule of probability. Now, once we have these language models, some of the problems occur. One of them is that you get lots of zeros, you get lots of sparsity. These cause problems. You end up scoring things and saying that they're impossible. And so smoothing is a way to deal with this. And finally, we'll talk about how we evaluate language models, so how we can say that a language model is a good fit, does actually characterize language well. Okay, so the idea is that we want to get a probability for a sequence of words. So think about them as sentences here. By and large, language models will be applied to things like sentences most of the time. So if we have an M-word sentence, we'd like to give it a probability. We'd like to give it a number. Now, you might think that, great, we can assign a probability to a sentence just by seeing how often that sentence has ever existed, how many people have ever said that sentence, versus the number of sentences that could ever be spoken. Now, if we were to do that, it's great if we have a really enormous sample of language so that we can be confident that all the sentences that could ever be spoken will have been spoken. But because we know that language, because we know our resources will be finite, we know that language has this recursive property, we can say longer and longer sentences, then we're never going to actually have represented every sentence seen. So were we to just estimate this as saying this sentence is a big chunk, how often is it seen? That's not going to really work. It's not going to generalize. People can say things in slightly different words, and a lot of sentences that you'll see will never have been spoken before compared to your training resources. So what we do is we use a chain rule of probability, as shown here. We have this big joint distribution over m things. M might be 20 or 30 here, say. And we're going to decompose it into these little steps. So we haven't actually done anything here formally. There's no sort of change in sort of the expressive power of the model. All we've done is saying that we're going to basically express the probability of a joint event by the probability of each of its component events. And you notice by the time we get to the end, we'll say probability of the last word given all the words from the beginning to the end. So you may sort of flag that, hang on, this last factor is going to be a monster to compute. It's going to have all the problems I just described. The first one's going to be easy, great. What are we going to do about this? And the answer to that is the Markov assumption. Yes?
Is it correct to say that by modeling the language as a joint probability, we're disregarding order?
No, we're not disregarding order, because if we have a sentence, say, the cat sat on the mat, we're saying the probability of cat, the probability of cat given the, so we know they're adjacent, probability of sat given the cat. So in each time we're sort of incrementally walking a window, expanding size window and generating the next word, and we always know all of the left context. So it's not symmetric in that way, right? If we were to say that we were only looking at every single word independently, then yes, we would be discarding order. But as soon as we look at least one symbol to the left, then we know that this adjacency is sort of giving rise to the order.
But that is just one way of factoring, doing factoring in different ways.
You could, yes. And the left to right mimics the way in which language is produced, the way in which language is heard. So by and large, it makes sense to think about it as a left to right decomposition. Sometimes we think about it as a right to left decomposition. That can be convenient at times. By and large, it tends not to work as well. Once we do the next slide, which is making a Markov assumption. So to deal with this intractability, if we're trying to estimate any of these probability distributions that have lots of variables involved, they might be on the conditioning side, they might be the event being produced. But as soon as we have too many of these, they end up being monsters to work out, right? To estimate from data. So for that reason, what we do is we say that any of these factors is going to then be approximated by only looking back a few words. So if we go back here, this guy was looking at the entire sentence, and instead of looking at the entire sentence, we're only going to look at the suffix of the sentence immediately preceding that word. So it's probably easier to see through any... actually, yeah, you can see it here through the formulation. So a unigram model, we're saying the probability over all of these words is just the product of the probabilities over every individual word. So in this case, we've thrown away ordering, and we've made it really simple. And this is the kind of thing you've seen in, like, Naive Bayes does this kind of trick as well, right? As a probabilistic model. A bigram model, now we're saying that we look at position I given I minus 1. And so we look at, notice I'm being a little bit tricksy here with my notation. I'm not dealing with the starting condition for the first one. I'm saying effectively there's something here which I'm going to call W0, which is set to some placeholder so that I can think about the first transition as a bigram, even though it is actually just predicting the first item on its own. And that way everything looks symmetrical as we go across the sentence. And in a trigram model, again, we're saying we're predicting the probability of each word given the two preceding words. So the cat sat on the mat, if we're saying the cat, and then we predict sat. Now we have 3 words, the cat sat, and we'll frame it this way. And we won't look any earlier in the sentence. So even as we get to the end of the sentence, we're still looking at the previous 2 words. Okay. So you should have seen these kind of things before, hopefully. This idea of having a big, nasty distribution using a Markov assumption to make it simpler. So if we were going to use maximum likelihood estimation, this is the standard off-the-shelf technique that you use for basically you're saying what's the likelihood of some data. Let's try and maximize the likelihood of that data to find the parameters. And the parameters here being these probability distributions. So this guy would be a 2-dimensional table. It has the vocabulary on one side and the vocabulary on the other. This one would be just a vector. And this one would be a tensor. So like a 3-dimensional cube here of parameters. Now, once we're looking at the trigram model, say, vocabulary to the power of 3, it's a lot of parameters. We have to try and estimate them. How do we estimate them? Well, if we go through this is not something that's part of the course, but if you look at, say, statistical machine learning subject or various subjects in stats, you look at how to derive one of these things, you end up with a fairly simple solution. And what you see is that the probabilities for unigram models are just basically the counts of how many times you've seen each word divided by the total number of words you've seen. So this is just a simple frequency, a normalized frequency. And similarly, if we look at, say, bigram model here, so if we're looking at the probability for words that come after a previous word, so a pair of words here, we're going to get the counts for the number of times that pair of words occurred, divided by the number of times that previous word occurred. So if we're talking about, say, cat as our previous word and our candidate word as sat, we're going to look at how often we see cat sat, divided by how many times we've seen cat on its own. And so if cat is a really common word, it has lots of things following it. Perhaps it'll have lots of other options other than sat. So the probability of sat given cat is going to be low. I should have chosen words that don't rhyme, because it just makes it hard. Okay, and in n-gram models generally, the same formula holds. In this case, we're looking at an n-gram, and here we're looking at an n-1 gram. This n-1 gram on the denominator corresponds to all of the events in the conditioning side, this probability distribution here. Okay. So that's nice and easy. Estimating these models is just counting. You just need to count how often you've seen all these variable length sequences. Once you've got the counts, you can get these values very simply. Okay, so another thing that we do before I get on to showing you it in practice, we have this special bookending, which is what I was alluding to before, so we didn't have to have a problem at the start of the sentence. We actually add one at the start of the sentence and one at the end of the sentence. So sometimes it's written as this S with angle brackets. Sometimes it's sort of more like XML style tags, so start end to a sentence. In the reading that I've assigned, it's shown as an open dot and a closed dot. There's special sentinel tokens that are extra to our vocabulary, and we'll put one at the start and one at the end of every sentence. And the point of doing that is that we can then slide our window of width n through the sequence, and that will give us every n-gram. So I'm giving you an example in the next slide, so I'll wait for a sec before I illustrate what I mean by that. Now, if we have a very high order model, we have to add n-1 of these special start symbols to the start, and we have to add one symbol to the end. Now, the reason why we add n-1 to the start is so that when we generate the first word, we have an n-gram. So the first word is generating the rightmost thing of that first n-gram. And then at the end, we have to know that we finished a sentence. So once we've predicted that we finished a sentence, once the model has decided that we finished, then we don't need to do any more. We have an n-gram that includes this termination character, which is our special symbol for stopping. Okay, so let me show you this through an example now. This is a very boring corpus. It had two sentences, which are yes, no, 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 yes, and this other one here. Because we're using a trigram language model, we're going to bookend it. We'll put two start symbols on the left of each sentence. We'll put one stop symbol on the right, as I described. And now, I'll just jump to this to explain. Whoops, that's not what I meant. So if we're working with a trigram language model and we have, say, the cat. Oh, that's terrible. That's pretty unreadable, isn't it? Wait a second. Better without the light. Oh, there you are. It's readable in the middle, but not at the top. Anyway, if we have the cat set on the mat. So if this is our sentence, we've put two start symbols here and one stop symbol there. The point being is that now for our trigram, if we then take a window of size 3, this is our first n-gram, this is our second n-gram, it's our third n-gram, and so on. And at the very end, we're going to get an n-gram that includes the stop symbol. So it'll be the mat stop. Once we've seen a stop, then we know that we have completed. And you can consider this sort of, if you're considering the process of actually generating the sentence. So imagine we're saying we're starting with just two start symbols. And we have to decide, maybe we're going to sample what the next word is going to be to generate. We're going to choose a symbol. Once we have that, now we can reveal it if we generated the, and we'll continue on. And now we've got the bigram context, so we can predict the next word because we can look up our table, and it's then going to have a vector of possible options. Sample one of those, and we'll keep going. And as soon as we hit the stop symbol, there's nothing more we need to do because this is our terminating condition. So sometimes these things are described as sort of the process of generation, the generative process. And this one just corresponds to generating one symbol at a time, left to right. And you were right, you could do it right to left if you chose. Or any other order, but it would be rather complicated how you parameterize the model if you did that. There are some crazy models like that in the literature, but I haven't exposed them to you to them. Okay, so in this case, we're interested, if this was our training data, what is the probability of this sentence here? Again, we bookend this one, and again, we're going to slide a trigram context through it. So the first trigram context is going to go from this start symbol to, whoops, click, to this yes here. And so you can see here, see, this is the first element in my formulation, right? So start, yes. Now, because of the conditioning bar in how we write conditional probabilities, they're not in the linear order that you'd expect. We've got the two previous symbols and then the thing being generated. So and then the next one is start, yes, generating no. So start, yes, generating no. and so on. And we slide this all the way across, and our last one is generating this stop symbol, given that we have a no yes context. Now, here I've got the probabilities. So to get these probabilities, you go back to the training corpus. In this case, you look at every context that included start something. There were 2 instances, the first word of each of these 2 sentences, and the 2 options were yes and no. So the probability of yes given start is half, probability of no given start is half. That's how we got this half. If we jump, say, to the end one, what's the probability given no yes of being the stop symbol? There's only one case where you have a yes after a no, which is here. Stop symbol is the only symbol that follows it, so the probability is 1 of seeing that. The probability of seeing no or yes is 0 here. Are there 2 no yeses? Oh. Ah. Yeah, you're right. Oh, then that should be a half, shouldn't it? Okay. I should have looked at this more carefully. Yes. Anyway. Okay. I'll revise that afterwards and make sure that it's actually correct. Okay. But the idea is relatively simple, what we're doing, right? So counting over the training set, normalizing or getting all these counts for trigrams and bigrams because we need them for the normalization, and then we're going to glue them together to get this thing. And we'll end up with a number saying how likely is this sentence? How much does this sentence look like the training set? And notice, well, assuming that this 0.1 is right, this sentence has never occurred in our training set, right? So it's assigning a number to something it's never seen before. It is generalizing, which is nice. That's what we needed to do. So what are some problems with this approach? One problem is that the language has very long distance effects. So if I have a sentence here, the lecture that took place last week was on retrieval. Now, if I said the lectures that took place last week were on retrieval, I need to change the verb from was to were here to make sure that it agrees with the subject. You can see, in order to capture that agreement effect, that the noun has to be singular or plural versus the verb here being in agreement, we need to have, I think, an n-gram n equals to 7, I think, in this case, right, in order to capture that. And of course, you could come up with other examples. You could put more stuff in the middle here. The lecture that took place last week on Tuesday, etc., etc. And you can make that arbitrarily long. So even if we choose large N, we're still missing a trick here, right? Language is a bit more complicated than this. This is a slightly impoverished model. It's an assumption that this Markov assumption is not really valid in many cases in language. We have to be aware of that. However, it's a very convenient assumption. It makes the models very fast, and the models can actually still be very powerful. So, but in general, we'll bias towards largest n. N might be 5, n might be 10, somewhere in that range often, in order to capture many of the effects that we do see in language. Another problem is the resulting probabilities are often very small. So as you saw before, we had, I don't know, what was it, 5 numbers or something we were multiplying together. In any real corpus, you're not going to get numbers around 1.5. You're going to get numbers around 10 to the minus 5 or something. Really tiny numbers most of the time. This n number is going to be infinitesimally small. Well, not infinitesimal, like still small, but not quite 0. In order to actually calculate it correctly, you're going to need to be careful with your mathematics, but you can do that very easily by working in log space. So this probability here, we can just say, well, what's the log of this probability? The log of the probability of the joint is the sum of the log of the probability of each of these components. Yes? If you're trying to greedily walk through and predict the most likely, then yes, you could throw away the context and say that it doesn't matter. It's just the next step that matters. If you are trying to score complete sentences, then it matters because you have to produce a number. So yes, Yes and no, I guess. And if you look at, so some algorithms, yes, you can throw this away. Some algorithms, you can just rescale all the numbers by constant to keep them in around the value 1, because you don't really care. And these kind of tricks do get used in practice as well. But usually the standard practice is to use logs, because they make everything a lot nicer. And because we're multiplying almost exclusively, it's actually easier to work with logs. So in translation, you might have a translation system that is producing a lot of candidate outputs, and you want to decide which one is the best. You're still comparing them, but they can be arbitrary lengths. They can have very different strings. They don't share a common prefix, potentially. If they shared the same prefix and it was just a question of what word came next, then it would be okay. But because they're radically different, then you need to actually get a full score of each, up to a constant. And you don't care what the constant is. So yes, there is some trickery you can do in that constant, but usually logs are the solution here. Okay, another problem here besides the sort of question of efficiency and, of numerical underflow is the idea of getting a probability for unseen words and words in contexts that are unseen. So unseen words, I'll come back to later. But the idea here is that if you've never seen a word before in your training set, what do you do when you see that later? And there are various hacks to get around this. You can read about them. I won't go into detail about the hacks. Usually you have a very, very large training set, so this is a relatively unlikely event. It doesn't occur too often. If you see words in new contexts, this is a very serious problem too. So for instance, in our example, like saying what words follow the cat, if we've got a fairly small corpus, then we're not going to have seen that bigram too often. We're not going to see that many trigrams containing it. We're definitely not going to have seen everything that would be a valid sentence. So we'd expect to see language later that had different words following, that had 0 count from the training set. And because we do get lots of zeros, we get zeros in some of the n-grams. When we go through and we multiply them out, if any of these ones gives us a 0, we end up with a 0 as our final thing, which means that it's useless for scoring. So if we had 100 machine translation outputs, we're trying to decide which was the most coherent. All of them had probability 0. It doesn't help. Now, one of them might actually have much bigger magnitude components in the other non-zero entries, but we don't know that because it's been all zeroed out. So we'd like to be able to deal with that. And smoothing the language model is the way we do that. And so that's what I'll get along with now. Yep? So it's a different order, but it's also, let me just flip to here. So if in the training set, if in the training set we saw the cat, read that, and there were various words that would follow this. We had sat, we had ran, runs, etc., right? Maybe we had just these 3, right? This occurs 5 times, 2 times, 1 time, for instance. Now at test time, we wouldn't be that surprised if we saw the cat escaped. But that was 0 at training time. So because if we had a trigram model, we need the count of the cat escaped. We get a 0, we get a probability 0. Now, we might have seen a cat escaped, or various other phrases that would give us good clues, or maybe escaped is a fairly common word in general. It'd be up towards the top of our vocabulary. Yeah, it's not that improbable, right? So we'd like for this 0 not to be too destructive and ruin all of our computation. Okay, so what can we do? We can smooth these numbers to try and stop them from being 0. The idea is that we've seen some events. So like in my example before, we saw sat, ran, and runs, but we didn't see escaped. We didn't see any of the other words in our vocabulary. And what we'd like to do is we'd like to steal some of the probability away from the things we've seen, and we'd like to give it to the things we haven't seen. And this is the idea of smoothing. So we're stealing probability from some bars and we're trying to allocate it to the others so that they're all, even if they're small, they're non-zero. And there are zillions of different types of smoothing. They're all trying to make sure that the probability is still valid, that it sums to 1. But there are lots of different ways you can do this, and I'll go through a couple of them. The dead simplest is the idea of adding 1 to every count. So if we were, let me just go back to here. So here we have sat, ran, runs, escaped, aardvark, whatever else, 0. So we'd have a whole lot of things here. We're going to add 1 to each of these counts, which might seem weird. You're saying, hang on, are we taking away mass? No, well, not yet. Let's wait a sec. And then for all of the ones that are 0, these are going to now become 1. So now instead of this guy being 5 divided by 8 originally, and this one being 2 divided by 8, this one being 1 divided by 8, as the probabilities once we normalize. Now if we consider over the whole vocabulary, now this is 6 divided by whatever this sum is, 8, 9, 10 plus vocabulary. 10 plus vocabulary minus 3. I'm just going to put big. And this one will be 6 divided by big, this one will be 6 divided by big, and this one will be 1 divided by big, right? So we can see here that we've gone from a situation where we had sort of a very big peak. Whoops, the first one was bigger than the second. We had some very big peaks, then a whole lot of zeros. And now we've moved to a situation where we basically have a little peak and then a whole lot of very low numbers grubbing along here, right, after we smooth. So, and this, bear in mind that this is vocabulary size, so this is like tens of thousands of different things here. So adding on 1 to all of the zeros is having a massive effect on this denominator. And that's why I've written it as big here, because it's going to dominate in any of the computations. Yeah, so that's what we're doing here. We're just adding 1 to every numerator. So if the count was 0, it becomes 1. If the count was 1, it becomes 2, and so forth. And because of that, to make it add to 1, the sum up to 1, the probability, we need to add this vocabulary factor at the bottom. Because there are vocabulary possible items that we could have tested. They all had 1 added. So in order to sum up the effect of that, we need to account for it on the bottom here as well. Similarly for bigram models, trigram models, and so on, it's the same trick. It's just in each case, we're having to add on the number of events that we've artificially inflated the numerator with to make it balance. Okay. Here's an example. The rat ate the cheese. If we look at the bigram probability of 8 given rat, based around this training corpus, we would see that it's originally count 1, but now we end up adding an extra 1 to it, so it becomes count 2. The probability of rat was just, or the count of rat was 1, but now there are 1, 2, 3, 4, 5. There are 5 unique tokens here, so we've added on 5 unique tokens, 1, 2, 3, 4, 5. But yeah, there's 4 unique tokens plus the special sentence end symbol, so I think that denominator should be 6 in my mind, because there are 6 possible, contexts here. In which it could be seen. So yeah, anyway, I'll fix that up later to make sure. And I won't dwell on it at the moment. But if we look at the point here is that the probability of 8 given cheese, they never occurred next to one another. So the count of cheese 8 is going to be low, 0, and now it becomes 1. And so now it ends up having some score under our probability. Okay, so adding 1 is pretty aggressive. As I was sort of illustrating with the bars suddenly shrinking because there's so much going on in the denominator. So often we might add a fraction k, and we can tune this by hand. We might use a tiny value like, I know, 10 to the minus 5. There are various other options. 0.5 is another option that's kind of quite widely used. So we have to be careful because this has a big effect. Okay, so the last method that I want to talk about is Kneser-Nye smoothing. So this is the state of the art from n-gram language models, like the most the method that generalizes the best to unseen test data. It's a fairly complex method, so I'll talk briefly about the 3 different ideas that underlie it. So the first one is interpolation. And it's the idea of saying that if we have a 5-gram model, instead of just adding events to things that it hasn't seen, we can look at what the 4-gram prediction might have been, or the 3-gram prediction, and so on. We'll go through that in a sec. Absolute discounting is the method it uses to work out, to smooth the probabilities. And instead of adding to counts, it actually subtracts from counts, and then of things that were seen once or more, and then it adds that back into things that were seen 0 times. And then it has this idea of continuation counts, which I'll discuss in a sec. Okay, so back off. So this is the idea of saying if we have a high-order model, it needs a lot of context, it's very sparse, so we're gonna try and use lower-order models to fill in for it when this model is not very accurate. So back off is one of the simpler strategies for doing this, and the idea is it's shown here. The notation gets a little bit more involved, but I'll go through some of the factors in a sec. So this is our trigram model, and we've put BO as a subscript here just to indicate that it's a back-off model. So the trigram model for back-off basically says, well, if we've seen the event in question, this trigram, and it's got a count that's non-zero, then we're going to use its standard maximum likelihood estimate with a little star, and I'll come back to the star. If we haven't seen this thing, so its count is 0, then what we're going to do is we're going to back off to the bigram model. So we're just going to use the bigram context now. We've dropped WI minus 2 here, and we're going to use this guy instead. Now, the caveat here that I mentioned before is that we need this to sum to 1. If we just did what I described, it wouldn't sum to 1. So in order to make it sum to 1, we're going to have to slightly munge the probability distribution here by multiplying it by some number that's less than 1. And we're going to have to allocate that mass to the back off here using this alpha function. And I'm not going to go into how you define them. They're absolutely horrible. The mathematics is really disgusting. And they're not that widely used in practice. Back off is the simplest one to understand until you try and implement it. And then it's really, really horrible, getting the sum to 1 probability. Yes? It's a function of those two variables because the amount of back off, the amount of mass you provide that you subtract from this guy to then reassign here might vary depending on the context. If it's a really common context, it's more likely perhaps to have a greater amount of mass removed, for instance. So interpolation is a slightly cleaner and easier to implement version, which is doing something similar. So the idea here is that we're saying we have a trigram model. We're going to say that this trigram model is defined as our raw maximum likelihood trigram model multiplied by some constant plus 1 minus that constant multiplied through by the bigram model. So it's a mixture between the trigram model and the bigram model. The bigram model here is defined recursively, right? This is P sub interp. So we'd apply this again for bigram versus unigrams. Now this constant here, again, for maximum generality, it's a function of the context. You could implement it just as a constant and use it the same across all different n-gram contexts. But oftentimes it's actually worthwhile having different amounts of interpolation for different contexts. For instance, if the context is seen a lot, then maybe you don't want to interpolate, right? You trust your trigram model. If the context is very rare, you don't trust it. You want to back off. Oh, sorry, you want to interpolate with the lower order model. Okay, so these interpolation probabilities must sum to 1. So this constant is between 0 and 1, this lambda. It can be constant, and this is what I just said. And the way we train these parameters, these lambdas, is a bit complicated. Expectation maximization is often used as the algorithm for fitting these to data. And I won't go through that. You can read about it if you're interested. Okay, so absolute discounting is the next component in Kness and I. So the idea is if we were to go about estimating the counts from a held out corpus, it actually turns out we'd end up getting quite different counts from what we got from training. And this is used to motivate, this is sort of the proof about the mechanism behind absolute discounting. And the idea is that we're going to take, we're basically going to take mass from from various n-grams, and we're going to distribute that to other unseen things. And the idea is that we end up taking most of the mass from lower count stuff and allocating it to zeros versus higher count things, then, okay, subtracting a constant is only going to have a very minor effect. And that intuition kind of matches the kind of thing you see when you do held-out testing. So what it looks like is this. So if we're looking at a bigram model here, here's the counts of our bigram divided by a unigram, the kind of normal thing you'd seen. The only difference here is we've got this minus d here. So we have this constant. Basically, we're saying if this count, sorry, I should be more formal. This is capped, can't go below 0. So it's got a lower bound on it. If the count is above 0, we're going to subtract off this value d, and then that value d is then going to be used in aggregate to decide how much we're going to then back off to this lower, or how much we're going to interpolate to this lower layer. So the function here, lambda, is going to be a function of this constant d. Okay. And sorry, this is the, okay, I won't go through that, but this is just showing the kind of observations you would see in practice between the different counts that you see in the training set and the different counts that you expect to see on a held-out set. And I don't know if you can read that well, but for high values, we go from 9 to 8.2. For low values, we go from 1 to 0.4. So by and large, they're somewhere around subtracting 0.5, 0.6 or so from the number. But notice how the zeros are now increased by a tiny amount. That in held out, we are going to see bigrams that we didn't see at training time. And so this is based around these observations, this idea of subtracting from all of these, a uniform of 1 plus all of this uniform number, and then adding it back into the zeros. Okay, so the last thing that they have is this idea of continuation counts. So the idea is that raw counts can be quite unreliable, and particularly when you see words that only occur in very specific places. So I've got an example here of Zealand, right? So Zealand is most often used as part of the phrase New Zealand. So if we're looking at the token Zealand, we don't really want to get too carried away with how common it is, because most of the time it's actually part of New Zealand. So it doesn't actually, it's not a very versatile word. It can only appear in very few places. If there's anyone here who's Danish, they might dispute some of the numbers on this slide, because I believe Zealand is the name of the island, one of the islands in Denmark, which is what New Zealand was named after. But anyway, let's just ignore that and pretend that Zealand only occurs in the context of New Zealand. So if we were predicting Zealand given old, that'll interpolate with probability of Zealand. It's going to give it a high score, largely, because it's a fairly common word. So we'd prefer it to actually be more, to penalize these numbers. And the idea is that we actually look at the frequency of the context in which it's seen, rather than the raw counts. So if we see that Zealand only occurs in one context, with new before it, we give it a special continuation count of 1. Versus another word like Indonesia. Indonesia is going to occur in lots of different contexts. It's going to have lots of strings to the left. So it's going to have a high continuation count. Okay, so if you throw all this together, I'm not going to go through this too much, but the idea is that we have this idea of doing the absolute discounting here. We're using continuation count, we're using special types of counts here. It's a continuation count for our numerator and our denominator terms, and we've got this special factor, which is a function of d, which is then going to affect how it backs off to a lower order. Okay, there's a slight caveat that this CKN is a continuation count except at the highest n-gram level. So if you have a 5-gram model, at the level of 5 grams, it's normal counts. At the level of 4 grams, now it's continuation counts, and so on all the way back. And I won't go into the details of why. And here's our definition of our lambda function. It's using d, but it's scaling it by the number of times this d has been used to massacre the counts. Right? So it's working out the aggregate effect of this subtraction in the probability formulation. I'm not expecting you to know this. I'm putting it here for completeness. Okay, so in practice, the best Kness and I method uses different disk things for different n-gram orders. It uses them for different n-gram contexts using a similar formula. There are a few modified versions of it that do something slightly different, but by and large, that's roughly how it works. And most n-grams are going to use 5 or so, sometimes up to 10 or 20 in very few specific cases, but mostly around sort of 5 to 7 kind of range. Okay. So now that I've talked about some models of language models, I want to talk about how you evaluate them. Now, you can evaluate them in 2 ways. You can evaluate them saying, how well do they work in spelling correction, right? So if I do have a model, a spelling correction model that says, this looks like a mistake, can I replace this word with another word, say with low edit distance? Here are a few candidates. Now, language model, tell me which one is most coherent. You can test and see how often it actually corrects the spelling in a way that would mimic what a human would do. In machine translation, you can use it to select from multiple machine translation outputs. And we'll see this when we talk about MT at the end of the subject. And see how well does the machine translation outputs, do they end up looking better? Do they end up being better translations? And today, though, I'll talk about the intrinsic way. And the intrinsic way of evaluating these is how probable does it think some unseen data is? If we gave it some test data that it hasn't seen before, does it think it's high probability? And the way we measure probability is with this thing called perplexity. It's just a convenient form of expressing the probability. Okay. And this is formulated as follows. It looks a bit nasty, but if we have a look at it here, so this is the way it's presented a lot of the time. This is another way of presenting it. They're exactly the same. The perplexity is basically the probability, inverse probability, and then we take the root to the power, or the nth root of this. And the idea is basically reciprocating the probability distribution. If it's 1 on 20, then we'll get the number 20. So how many events do we expect? And then we average it by taking the mth root, because there are m terms here that have been producted together, right? So m words in this distribution. So we're saying, what's the average number of symbols we expect to follow each context as we go through our test set? If we get a very low number, like a value 1, then we're basically saying the model was perfect. It predicted only one symbol each time, and that was the correct symbol. If it was terrible, then it would assign the correct thing 0. It would end up with an infinity, and we'd have an undefined perplexity or an infinite perplexity. If it was a uniform model, then each probability would be 1 on vocabulary. So we'd get 1 on vocabulary reciprocated. So I've got vocabulary m times. So vocabulary to the power of an m to the root m gives us just vocabulary. So a value of perplexity equal to the vocabulary size tells you that your model is a uniform guesser. It gives you sort of a threshold to understand these numbers. And that's why we do it this way, so that you can sort of interpret to see how well you've characterized the problem. Now, there's the unknown word problem here as well. If there's an unknown word, its probability will be 0. There are various hacks to get around this. One is to omit them from the calculation here and just report, this is the perplexity, there were 5 unknown words in our test set. Another one is you map them to a special token, a bit like our start and end symbol, and we make sure that that token is seen during training, and they get a very low score. And that's the technique that tends to get used in neural world these days, which is another hack. If we're looking at perplexity scores, here's some examples from a paper of mine, creating language models. I'm just illustrating that we can go. So here are some language models that were over 4 different languages. Well, each row is a different language application. We tried language models at size 2, we call them m-grams. I think we use n for something else. Between 2, 10, and this is our fancy approach, which didn't need to have a limit, so we could send it towards infinity. And we can see that in this case, each time the perplexity is decreasing. As we increase the order of the model, it can characterize the data better, and it can get a better fit. It's giving you an idea of the kind of values that you get in practice. You can apply this at the word level. You can also apply it at the character level. So in this case now, we apply to, say, 20 grams, for instance, over characters, and you can get quite good improvements as you get larger and larger. But you can imagine here, once we're talking about 10 gram and 20 gram models that have quite a few parameters, they end up being quite complicated. This is something to be aware of, that the engineering behind doing some of these things can get quite advanced. Incidentally, sort of, I guess Matthias did talk about this. So this was a joint work with Matthias, who was giving you the lectures on IR. We were using a whole lot of suffix trees and so on to represent all of the n-grams and contexts and getting all of the quantities we could out of suffix trees and suffix arrays and so on, which is how we did this over very large data sets and without language model order requirement. Okay, so the last thing you can do with these, and this is kind of a fun thing, is you can start with an initial word, and then you can sample the following word. And then given those two words, you can sample the next word. And you can keep going and sample until you reach the end of sentence symbol. And then you can output this as a potential example of language. And here's a couple of examples. I can't remember what order language model we were using, but we were priming it with the first word and then letting it continue. And you can see in the first case, it's got into sort of fairly archaic language, and then it's got into this rut and continued creating things in this kind of style, which is kind of cute. In this case, it's getting towards a more sort of numerical, financial kind of type of text, and it's continued in that vein. And actually, this is kind of interesting. I don't know if you've been following the news. There was a paper by OpenAI in the US. They're a sort of startup that does a lot of AI, and they were claiming their language model was so good that it was dangerous, and they didn't want to release it, which I think is incredibly stupid. But they made a lot of headlines and a lot of press by doing it. It's kind of stupid because people have had language models that could generate to a very similar standard for many, many years, and it's important to make your work reproducible, so it's very strange for them to hide it. Anyway, so let me finish up. So n-gram language models can capture the predictability of language. They make a few assumptions that make it a little bit easy for us to deal with. We can get the information required to do them. I say unsupervised here, but the point is we don't need explicit labeling or anything. You just need text, you just need to tokenize it, and then you can run your language model. You do need to think carefully about smoothing. And so CANES-NI is a very nice method that has a lot of smoothing implicit in the model that can then cope with sparsity problems. And sorry, I shouldn't have that last point because it's coming up in the next lectures that we will see in next week about distributional semantics and lexical semantics. I just want to say one word on the reading before we finish up. So I had written something else, but I think this one's a lot better, so I swapped it over. So please take a look at the Eisenstein reference, which is, covers this very nicely. He also covers neural language models, which we'll be covering later, so you're welcome to read 6.3 if you like. Thank you. Okay.